Good evening, students. My name is Shashank Shekhar, and we are doing a crash course on chemistry of 45 days for the upcoming JEE exam. And today is our 32nd day. Today we will be starting our new chapter, that is hydrocarbons. Let us start this chapter, which is hydrocarbons. So it will be of two parts, part 1 and part 2. Hi Siri. Hello. So this is the JEE syllabus that is given by the NTA. So you can see here we have this alkane, alkene, alkynes. So today we will be covering all these two, okay, and the remaining alkyne we will cover tomorrow. So let us start this. Before starting, let me make one thing clear here that I have covered this isomerism part in the previous class in the previous chapter also. So we will not seeing this, okay, and the nomenclature also. So mainly our focus will be on alkane and alkene, and what are the general methods and preparation, and what are the chemical reactions that they undergo. So let us start the first one. So before that, let us see the weightage of this chapter. So an average of one question come from this chapter and it has a weightage of 4 marks. Then this is all the topic that we'll be covering today. So you can see here that there are many preparation methods that are given in this topic to be covered. So let us start this thing. So first of all, let us see what are hydrocarbons and let us see what is their classification. By saying hydrocarbon, we mean that we have a bond between C and H. So it is basically a compound that is formed from the interconnection of carbon and hydrogen and many other elements also like nitrogen, oxygen, and sulfur. Now, if you see their classification, then hydrocarbon are of three types basically. The first one is saturated, second one is unsaturated, and the third one is aromatic. So, what are saturated hydrocarbons? So, saturated hydrocarbons are mainly which do not have a double bond. So they do not have a double bond. So they can be of two types. The first one is cycloalkanes and the second one is aliphatic. So in cycloalkanes we generally have all those like which are cyclic in nature. Now in aliphatic the open chain structure are called aliphatic one. Okay. Now the second one is unsaturated. The unsaturated mean they have a double bond between them. The first one is saturated, unsaturated, and the third one is aromatic. So this is the interesting part in this classification is that this is the aromatic part. So we will discuss in detail what are aromatic compounds and what thing that make them special from all other compounds. So today we'll mainly focus on saturated and some parts of unsaturated. Now before moving to that, let us see the what is projections. So what are projections? So we have covered this projection part in the previous class also. So today basically I will be giving you a trick by which you can convert from this projection to this projection to this projection. So we will see how can we convert this projection, interconversion of this projection from one form to another. So if we consider a compound here, say like this, that is ethane. So this is ethane. We can have hydrogen, hydrogen, hydrogen. Now let us substitute one of the hydrogen with methane. Here also. Now we are not mentioning here the stereochemistry. So let us see what is the stereochemistry of this. So let us take an arbitrary stereochemistry. Suppose this is on the solid, this is on the wedge. Here also we have this similarly like this. Now if you want to change this to, say, we can change this to Sohars, we can change this to Newman. So first let us start with the Newman. So you can see very well that this CH3 is pointing towards me and this carbon, so we will take this carbon as 1 and this one as 2, and we will put this first carbon in front here and second carbon at the back. Okay, so here is the CH3 that we have, here is the H, and here is the H. So let us draw the dash wedge from this structure. Now, if you look at this structure, if you take the side angle, so suppose this is the middle bond between the both of the carbons. Okay, so this is the middle bond between both of the carbons. Suppose this one. Now, this CH3 is supposed to be in the plane. Then this hydrogen will be pointing towards me. So if you just rotate this like this, okay, so suppose this is the rotation, and after that this hydrogen points towards us. Now if you compare it to with this one, then this CH3 is trans to this one. So we will keep this CH3 trans, or you can say opposite side to this one. Now similarly, it has a hydrogen that is pointing towards us and one towards backward. Now the difficulty comes with the Fisher projection. Means for Sohars and Newman, it is quite visible that you are converting from this to this. But to convert into Fisher, we have a problem because Fisher looks like this. So if you see here, so this is the Fisher projection that we have, and all the vertical lines that these are the vertical lines that we are, sorry, horizontal line that we are having, that are present on this dash, sorry, wedge one, and this one is present on the like this kind of projection. Now if you want to convert this one, say we are converting this one into the Fisher projection. So how we'll do it? So let us do this. So first of all, I will write this one in this way. Okay, so I will write this one in this way. So we will write this one like this. Just CH3. This is the H. Suppose this is OH, and this one is also OH. Now this will be OH, and this will be H. Okay. Now we'll see this L. We'll first put this which are on the straight line on a single way. So we know the Fisher projection, it is like this. Let us erase this. Draw a straight line. So we will put all the means single line on the single bond. So it will be like this CH3. Now we will see that this L is projecting where? Okay, so this L is projecting on this side. So if it is on the left side, then we will put this thing on the left side, means which is pointing down. So this is on the so we will put it on the left side. So sorry, this is on the right side. So this we will put this dash one on the right side. That is CH3. That is H. Sorry, and OH on this side. Now this straight line is this CH3 is pointing towards left. Now in this case we will just take the opposite one. That means the wedge one will be on the left side. So since this is on the left side, so we'll put this wedge one on the left side and H on the opposite side. So in this way you can convert from the dash wedge to the Fisher. So this is a shortcut, you can apply it, so it is very useful one. So if you want to check, you can check the RS configuration on both this point and check whether this is equivalent to this or not. So this was the conversion from this, and I'm not going to discuss this part because I've discussed in the previous class also what is Newman and Sohar. I will just focus on this conversion part. Now let us move to alkane. So we will start with the preparation of alkane. So before that, We will see some properties like the physical properties of alkane. Physical properties of alkane. So here are some points you should remember. So highest is the molecular formula, means the molecular weight, because these alkanes are normally non-polar, so they do not have any kind of polar interaction or anything. So they will just have this van der Waals interaction. Van der Waals interaction. And we know very well that van der Waals interaction is directly proportional to the size. So greater will be the molecular weight, greater will be the boiling point of this alkane. So it is directly proportional to boiling point. Second one, as the branching is supposed to have the same molecular weight, then in that case, the one having the least branch will have the, means branching is inversely proportional to this. So if you like it like this, for same molecular weight. So as long as the molecule is non-polar, so we will just consider the van der Waals interaction. So the one which is having the greater molecular weight will have the higher boiling point. Okay. And second, as the branching increases, the boiling point decreases. Okay. Now let us move to the preparation of alkane. So the first one is reduction of alkyl halides. So here we have the reduction of from alkyl halide. First from the zinc. Then second we have this lithium aluminum hydride, which is used as a reducing agent. So all these are metals. Similarly, we can use tin here also. Then moving to this Woods reaction. So in Woods reaction, basically what we are doing is that we are taking an alkyl halide and we are using a metal that is sodium, and we are getting this as RR. Now if we use two different R, suppose we are using two different R like R plus R dash plus Na 2Na, then we will get R dash. But in that case, suppose this is having X, this is also having an X. So this reaction we will call as Woods fatigue reaction. So if both the alkanes are same on the single bond side, then it is called Woods reaction. And in case of different alkane, we will call it as Woods fatigue reaction. Now, third one is hydrogenation of alkene. So it is a metal, you can say metal catalyzed reaction. So this is the catalyst that we have here. Now it follows a simple adsorption method, means this alkene first gets this hydrogen is first adsorbed on this platinum metal, and then we add this alkene, which is getting reduced to this kind of compound. Now the thing that is to be noticed here is that it always forms a cis kind of alkane. So the configuration of this means both the hydrogen will be on the same side, added on the same side. Now the next one is the Corey-House reaction. So what is Corey-House reaction? Basically we are using a Grignard reagent or a lithium alkyl halide, alkyl lithium, and we are treating it with copper X and Rx. Then we are getting an R dash. So this is kind of transmetallation. So it is similar to the Woods reaction. We are changing just the metal here. We are using magnesium or lithium in place of the sodium. Okay. Now next is decarboxylation. So what is decarboxylation? So we are using a salt of carboxylic acid. So here it is sodium acetate, or suppose it is CH3, then it will be sodium acetate. And then we are reacting it with sodium hydroxide. Then we will get the CH4 if it is CH3, and then sodium bicarbonate. Then we have the Kolbe electrolytic method. So here we are using the potassium salt of this carboxylic acid, and then doing its hydrolysis. Then we will get this RR on one of the electrode, and carbon dioxide and H2 will be released, and KH on the another electrode. We can also use the halogenation method. So in halogenation method, we use the photos means it's a photo reaction. So first, this Cl gets dissociated with the help of H nu, which is light. So this is the initial step we have, and we will get two Cl radical. Then this Cl radical will react with this CH3. Okay, this will react with CH3 to give us CH3 dot and HCl. Now this CH3 dot and Cl will again react, and we will get the CH3Cl alkyl halide. So this is the halogenation of this alkane. Now in the termination step, two Cl radical react and give Cl2. Again two CH3 react and give CH3 2. And here CH3 dot and Cl dot react and give us CH3Cl. Now next we have this nitration. So in nitration of alkene, what we do is we heat this alkane with nitric acid in high temperature, and we will get this methane nitrile plus water. Then this is combustion. So combustion of any alkane gives us carbon dioxide and water plus heat. Now next we have this aromatization. So if we are taking a cyclohexane, okay, we are taking a cyclohexane. So taking a alkane that is 6 member, and we react it with V2O5 CS23 or any of these oxides. Then at high temperature and high pressure we will get the benzene ring. Then again, if we take an alkane, okay, if we take an alkane and react it with KMnO4, then we will get a tertiary. So we are basically here we are taking a tertiary alkane. So it is having 3 R's attached to it, 3 carbons, and we will get it as R3COH, which is a 3-degree alcohol. Next we will move to alkene. So I will start with the heat of hydrogenation. So heat of hydrogenation is basically the amount of heat that is released whenever a alkene is added with hydrogen in the presence of metal. Again we are using here the same thing. For the preparation of alkene we are using the alkene. Now we are seeing the reactions of alkene. So this one is so this heat of hydrogenation is dependent upon the alpha hydrogen. So more is the number of alpha hydrogen, the heat of hydrogenation increases. Why? Because as the number of alpha hydrogen increases, the number of hyperconjugation structure increases, and more heat is released during the reaction. Now we have cracking of petroleum. So we are reacting this alkane, and we are in the presence of petroleum and getting this alkane. Second, we have this dehydrogenation of alkyl halide. So when we are taking a alkyl halide and reacting it with a alcoholic KOH, okay, so we are reacting with alcoholic KOH, then we will get the alkene. So let us start with some questions. So we have some questions that are here. So this is the first question. The trans alkene are formed by the reduction of alkyne with. So which one of this will give trans alkyne? So if we take the H2 case, then this will give us cis. Why? Because, so suppose this is a simple mechanism. If we are taking a simple mechanism, I am not going to the complexities. So suppose this is the metal surface that we have. Now initially this hydrogen is attached on this surface. Now they are say attached to this surface by van der Waals interaction, simple van der Waals interaction. Now if an alkyne comes here like this alkyne reacts and both of this H is added, and we get a type of activated complex, and both H are added on the same side. So it gives us cis kind of alkene. Now this Na, if we see here Na here, so it add like this. So suppose this is the Na, so it has a free electron. Then we have this alkyne, and this is the anti-bonding that we are having. So it will donate one electron here. So we will go through a radical reaction, and this kind of intermediate is formed. Okay, this kind of intermediate is formed. Now since both these radical are on the opposite side, means it is a kind of anti-periplanar, then both the hydrogen gets add on the opposite side. So this is the correct answer. So it will give transalkene. So sodium metal reduces alkyne with anti-stereochemistry to give alkyne. So same thing is written here. The reduction is selectively anti, since the vinyl chloride during reaction is more stable in trans configuration. So this is the kind of reaction that we are having. Okay. So first this nit and sodium is giving one electron here, and both of this bond pair is shifting on this carbon, and we are getting a anti-parallel type of stereochemistry. Now it will take one NH from here, and you will get this trans one. Now which of the following is the predominant structure in the reaction of HOBr with propene? So if we look at the addition of alkene, so it can add this HBr in two ways. First is the Markovnikov, and second is the anti-Markovnikov. Now what is the difference between Markovnikov and anti-Markovnikov? So in Markovnikov we simply use this HBr, it goes through a radical reaction. But in case of anti-Markovnikov, we use the peroxide plus this HBr, and it goes through formation of carbocation. Now what is the difference between the products? So if suppose this is the alkene, then suppose this is the alkene, then Br is added on the less substituted car side, less substituted side, where it is this bromine is added on the more substituted one. Okay, so this is the difference between the both of these reactions. So let us see what is the question here. So which of this is predominant product in the reaction of propene? So it will follow Markovnikov's rule, as we are using no peroxide here. So we'll simply get an Br on the less substituted side. Which compound will give this 5-keto-methyl upon ozonolysis? So it is asking that which of this compound will give 5-keto 2-methyl hexanal. So if you look at this compound, hexanal, so we have this 6 carbon, 1 2 3 4 5 6. We have the 5 keto, so 1 2 3 4 5 keto, 2 methyl, so if you know the what is ozone. So suppose this is the alkene we have, and if we add ozone here, then we will get 2 moles of aldehyde in this reaction. Okay, and it is hexanal, so first is the OH. Now if you do the reverse reaction here, that means it is added on this side. So we have a double bond here. So if we name it 1 2 3 4 5, so 1 and 5 are attached from double bond. 2, 3, 4, 5. Now this 2 is having the CH3 and this 5 is also having a CH3. So we are having this kind of, so this is the correct product. Okay, so B is the answer for this. So if you see all the hydrolysis reaction, so if you do the hydrolysis here, we will get you have one O here and one O here, and if you open it, you will get this one. Similarly, if you look at this one, so we are reacting with ozone, so we will get one O here and one O here. Okay, so this is the correct answer. So this is fourth question. So arrange the following in the order of stability for the following molecules. So for cyclohexane, the structure which will be stable in which the methyl group is on the axial position. So both of the methyl group should be on the axial position. So if you see here, so this one is in the axial, but it is on equatorial. So it is not stable. This one is not stable. So in this one we have this axial here, but this is on equatorial. So it is also not stable. For the third one, both of the methyl are on the axial one. So sorry, the equatorial one. So it is the most stable. So this is the correct answer, third one. Okay, so third one is the most stable. Then we have the first, then second and fourth. Fifth question. So what is the best way to carry out the following transformation? So we have to prepare one pentyne to pentanol. So how we can do it? So the first one is basically adding this pentyne. So this is the reaction that we can carry. So first we will react this with BH3 and we will get an anti-Markovnikov. So why is this anti-Markovnikov? So if you look at this, say this is the reaction that we have. So if we add BH3 to it, we will get this type of first one. Similarly, each H will be removed by one H. Okay, so like this. Similarly, this one also. Now upon hydrolysis, the OH will come here, or the O will come here in this case, because OH will come at this place. Suppose this is the OH we will get here, but on since this is not much stable, because we know that keto form is more stable than the enol form, so we'll get this as aldehyde. Now upon we will not I will not give you the answer. We'll just do the questions. So which one has the minimum boiling point? So I've told you earlier, for deciding the boiling point, we will simply see first of all which one has the higher say boiling point, which has the higher molecular weight. So we'll just see which has the higher molecular weight. After that, we will see that which one has the smaller number of branches. Accordingly, you can arrange this in the increasing order of boiling point. Now, butene 1-ene may be converted to butane by reaction with. Okay, so we know very well that this reaction can be used PDH2. Question number 8. So ozonlysis of an organic compound gives formaldehyde as one of the product. This confirms the presence of two ethynylic double bond, one vinyl group, one isopropyl group, one acetyl group. So ozonlysis of an organic compound gives formaldehyde. So what does this represent? So it can represent that we have one double bond. First of all, we have one double bond. Okay. Now since you are getting the formaldehyde, means the double bond is having no branches at all. Means it has only two carbon attached to this double bond. Now it has an isopropyl group. No, nothing like that can we get from here. Two ethynylic double bond. Yeah. So this is the correct answer. Now which of the following reaction will yield 2,2-dibromopropane. 2,2-dibromopropane. So if you see here, first this will go two types of, means this alkyne can go HBr addition two times. Okay, this one can give us CH3 C H. So here first Br will be added, again one more Br will be added here. So this is not the answer. Then we have this CH3 CH CHBr. So Br will be added here only. So it is asking we have to get 2,2-dibromopropane. So it is not the answer. So it is also not the answer. Okay, so this one will give us the correct answer. So this is the correct answer that we have. C. Now question number 10. When 1,1-dichloropropane and 2,2-dichloropropane are reacted separately with alcoholic KOH, compounds A and B are formed. Both A and B gave the same product C on reduction using amalgamated zinc and HCl. Identify C. So if you see here, we have two of the reactants, that is one dichloropropane. Suppose this is the propane, and two dichloropropane. Now this both are separately reacted with alcoholic KOH. Okay, so this is reacted with alcoholic KOH. So what we will get? This here also. Now again one more will be reduced. We will get this as alkyne. So we will get two alkynes, that is this alkyne and this alkyne. Now both A and B give the same product C on reduction using amalgamated zinc and HCl. So you will react this with zinc and HCl and you will get your product. So these were the questions for today. So if you have any issues, you can ask. So before ending this lecture, so let me make a brief of this whole of this chapter. So first we have seen that what are alkanes. So alkanes are basically which under saturated compounds, and they can be prepared using numerous methods. So the first one is using the alkyl halide and all. So let us just revise this one. So before that, let me see what how can we convert from one structure to other. Okay. Suppose this is the carbon that we have here. This is a CH3. Suppose this is the H. This is the OH. Similarly, suppose this is the OH that we have here. Suppose it is CH3. We have this C2H5. Okay. Suppose there is this C, H, CH3 and OH. Similarly, we have this OH, H and C2H5. So this is the conversion. So if you want, you can convert from this eclipse to this staggered to this Newman projection, and then to this Fisher projection. So this is the Sauer, this is the Newman, and this is the DLN configuration, which is the also called as Fisher projection. Okay. So this is the eclipsed one. This is the staggered one. Why? Because this H is not in front of this, so it is the eclipsed. Sorry. So this is the staggered in which H is not in front of this H, but in the eclipsed one we have this H in front of this H. So it is kind of eclipsing. So this hydrogen is eclipsing this one. This is eclipsing this one. This one is eclipsing this one. And similarly this is eclipsing this one. But if we see this one, so in this case there is no hydrogen that is present beyond of that. Similarly for this hydrogen there is no hydrogen that is present beyond of that. Okay, so this is a staggered case. So there is no kind of bond repulsion between the both of this hydrogen and carbon bonds. So we can convert this source into Newman also. So what we will do, we will just turn this around like this. So we are seeing from a you can say from this way. Now we'll turn this like this, and this carbon will come in front of in your face, and this carbon will go in the back. So suppose we are doing it for the sorry, we are doing it for the staggered case. So if you see for the staggered case, so there is no hydrogen that is present beyond of this. Similarly, here also no hydrogen is present beyond of this. So this is the staggered case. And for eclipsed, one hydrogen is present in back of the all of this. Now if you come to this Fischer projection, the most we are arranging this DL configuration in such a way that the most means oxidized carbon is placed at the top number, means here, or we can say here. So this is the most oxidized carbon, and the least oxidized carbon is placed here because it is the more number of hydrogen, so it is the least oxidized, and since it has the least number of hydrogen, it is the most oxidized. So in this way you can draw the Fischer projection. Now we use this alkyl halide in two ways. First we use in using metals, and then we can have this Woods reaction to do the same. Then we use the hydration of alkene, where I said that it will give us cis alkene. Now we next move to this Corey-House reaction. So we are basically reacting a Grignard reagent with this CuX and getting RR dash. Then we move to this decarboxylation mixture of sodium salt. So we are using first of the sodium salt at the sodium salt reacting with NaOH. So suppose this R is CH3, okay, and we are taking sodium hydroxide. We can also take this CaO also. Then we will get the methane here plus sodium bicarbonate. Now if we use this potassium, we will call it as Kolbe electrolysis method, and then we do the electrolysis of this salt, and you will get the RR here. So here you are putting H2O because we are doing it in the presence of water. Then CO2 and H2 gas will be released, and KOH will be formed as another electrode. Now we have this halogenation reaction here. So in halogenation, this is the basic reaction. So we are taking a alkane, reacting it with the halogen, and we are getting the alkane here. Now if you see the reactivity, the F2, then the Cl2, Br2 and I2. So what we are doing is first we are initiating the step by by introducing this chlorine gas in presence of heat. So it will give 2 Cl radical. Then upon that this Cl radical will react with methane and give us CH3 dot, and this again NHCl. Then this CH3 dot will react with this Cl and give us CH3Cl, which are required haloalkane plus this Cl radical. At the termination step, 2 of any radical will react, like Cl radical will react to give Cl2 gas, CH3 radical will react to give this ethane, and Cl radical will react with methane to give us methyl chloromethane. Now next we have this nitration. So in nitration reaction, what we are introducing a nitro group in the methane. So it is done at high temperature, that is 400 degrees Celsius, and we are reacting it with nitric acid with methane, and we are getting methyl nitrile plus water. Now next is combustion. So in combustion what we do, so if we react any alkane with oxygen, so we will get carbon dioxide and water plus heat. Okay. Similarly we have aromatization here. So in aromatization we are doing forming an aromatic ring. So in this case we are forming a benzene ring. So we take an alkane here and we react it with V2O5 or CH2O3 or any of this oxides, and we get it as methane. Now the thing to notice here is that we need high temperature and high pressure. Now oxidation of 3-degree alkane. So oxidation of 3-degree alkane in the presence of KMnO4 gives us 3-degree alcohol. Now moving on to alkene, so we have heat of hydrogenation. So the thing here to notice is that more is the number of alpha hydrogen, more is the number of more is the heat of hydrogen heat that is released. So this is for butene, this is for cis 2 butene, this is for trans 2 butene. So since we know that cis 2 butene is less stable, so it will give a less amount of heat. So it will give more amount of heat. Okay. Now cracking of petroleum. So if we take a petroleum and we heat in presence of PD or PT, then we will get the alkene. Okay. And the dehydrogenation of alkyl halide. So what we do is the take a alkyl halide and react it with alcoholic KOH, then we will get a alkene. Okay, so that was for today's lecture. So thank you for attending today's lecture. So tomorrow we will be seeing alkyne. So what we will see tomorrow is alkyne, and in alkyne we will see which is about its acidity and basicity. Then we will see the aromatic compounds well. Okay, thank you for today's lecture.